Hello. In this video, I'm going to be presenting a really interesting paper regarding hardware verification called Fuzzing Hardware Like Software. And I was initially drawn to this paper because I've done quite a bit of hardware design for my research, and I know from personal experience that testing and hardware verification in general can be a huge pain. And this paper offers a really clever way to make that verification process a lot less painful. So in this presentation, I'll try to cover all of the necessary background about hardware verification, and then we'll work our way up to the key idea of the paper. And then near the end, I'll talk through some of the challenges and the high-level idea behind the solutions they came up with. So to understand the challenges of verification, it's helpful to go over some basics of hardware design, specifically what a hardware description language is. So you can see in this little excerpt here, there's some system Verilog code, and this is one of the types of languages that hardware designers use to specify digital logic. So you can see that it looks vaguely like a C-style language, but there are a lot of kind of hardware-specific constructs that allow you to manipulate things like registers and logic gates, that type of thing. And you can see that people refer to this software side as pre-silicon because you can still patch things and fix bugs in that stage, but then there's a process called tape out where you're actually mapping this hardware description language to a netlist and then eventually transistors on an integrated circuit or something. And after that, it's called post-silicon because even if you find a bug, there's not really much you can do in terms of changing the physical layout or connections between the transistors. So you can see that this makes hardware pretty finicky and very important because it's easy to screw up, and then it's supporting the entire software stack above it. And this problem of it being difficult to verify hardware designs is something that's only getting worse because hardware designs are becoming more and more reliant on these IP blocks, which are bits of HDL or that do a very specific task really well. And while this is great for performance reasons, it also makes it so that the state space of the design blows up, and it's very, very hard to make sure that not only each individual IP block is bug-free, but that there are no weird interactions between all of them when kind of integrated into a full system. So, I mean, if one of these IP blocks has some issue, then it's possible for that to cascade into the whole stack kind of falling apart. And even if you have some sort of formally verified software sitting on top, it's possible for the security guarantees of that to be undermined because it's running on faulty hardware. So because of this, hardware engineers spend most of their time on verification versus implementing, just because the stakes are so high if you mess up and there's not really a way to fix it. So how do designers typically handle verification for their designs? Well, you can imagine that it's pretty similar to software, where you might have a design under test that takes various inputs and should deliver various outputs, and then you come up with a list of like inputs and then their expected outputs. And in hardware, you usually call this a test bench. And then you put this design under test in your test bench. On the left side, I'm showing like the test generation, on the right side, the evaluation, and you run this whole thing in a hardware simulator that is meant to be accurate to how the hardware would perform if it was actually taped out. So the big issue with this type of approach is there needs to be some kind of designer that is thinking about all of the tests that you're running the DUT on, and then also they need to know what all the correct outputs for those inputs are. And you can imagine that this is super labor intensive, and if the designer misses something, it's over, and also just doesn't scale well to larger designs that might not be able to, it's not possible to think of all the edge cases for a very large design. So because manual verification is so time-consuming, a strategy that designers have come up with is something called constrained random verification. And the way this works is you replace that manual test case generation with some kind of random test generator that is constrained to produce somewhat meaningful inputs for the design under test, but is otherwise kind of free to generate whatever inputs. And then you have a test evaluator that is checking whether the design under test met certain invariants that the designer expects the design to follow. And alternatively, you could kind of implement a known correct software model of the design under test and compare against that. But sometimes that's not always possible. So the big benefit to this strategy is it scales well to big designs. You could imagine like the programs can generate tons and tons of tests in a way that needs very little human supervision. In that way, you can kind of get this kind of big coverage, but unfortunately, it's largely surface level coverage because there are certain constructs in hardware design like finite state machine where there might be a long sequence of inputs needed to reach a certain state and visit certain edge cases of the design. And it's just kind of vanishingly improbable that a random test will actually kind of reach those edge cases. Unfortunately, that's where a lot of important and subtle bugs kind of hide that need to be found during the verification process. So you can see if you put the strategies we know so far on this kind of two axes, manual verification sits here where it doesn't really scale well to bigger designs just because of the human bottleneck, and then also kind of its surface level in that humans can't come up with all of the edge cases. And then we have constrained random verification, which kind of is even more surface level, but at least scales to larger designs. So the next type of strategy is actually the polar opposite. It's called formal verification. It kind of sits here on this spectrum, and you can see that it's very thorough, but has a really hard time scaling to larger designs. So the high-level idea of formal verification is you're just doing a very careful inspection of the design under test and trying to make formal, proven claims about the nature of that design. So the way that these typically start is you start with kind of all possible logical states that the design can be. That means 2 to the power of however many registers. and then you make some assumptions and assertions that will define what you consider a valid state and an invalid state. And the idea is you slowly whittle down all logical states to be constrained within only states that you've either marked as okay or invalid. And then you start with the initial state and you actually trace through this whole web of different possible outcomes, and you're just trying to make sure that you're never having a valid state transition into an invalid state, because that means the design isn't doing something correctly. So there are ways that make this a little bit more computationally tractable than actually brute forcing every single path, but still there's this state space explosion where if you have a big enough design, it just won't be able to formally prove that it's correct. So that's why designers have largely only used this for smaller designs. So coming back to this map of verification strategies, you might wonder if there's anything that sits in this kind of thorough testing plus big design region. And one kind of promising candidate that's been explored a little in the past is coverage directed test generation. So I'll explain that now. So the high level idea of coverage directed test generation is best explained for software. So I'm gonna pretend for now that this design under test is software, and you can see that we can color this like source code or the machine code using like red to mean something that hasn't been covered yet in terms of testing, and then green being something that has been covered. And then as you run the tests, you can measure which tests are actually leading to more of the overall code getting covered. And then if you feed that back into the test generator and mutate those kind of good tests that are covering more of the code space, then you can kind of iterate over and over until this feedback loop has fully covered all of the code. And at that point, you're done. But of course, this isn't really possible in reality because, of course, the design under test represents a circuit, and it's not like you can actually directly execute a digital circuit. So the issue is that hardware isn't software. So the way that prior work has handled this is by integrating some of the attributes of coverage for software into the actual hardware, into a more traditional test bench. So you can see instead of having a normal test bench, you make this custom coverage tracing test bench that's able to support this coverage tracing. And then you also modify the design under test to have instrumentation that's capable of capturing things like coverage. You can imagine this is a pretty custom and time-consuming process because it's not really obvious how you might even track coverage for certain circuits because it's not like lines of code. Plus, even if you're able to have the designer kind of instrument the design under test and make this custom test bench, you still have to run this through a hardware simulator. But using hardware simulation, now you can kind of complete this full feedback loop where you have a coverage-based test generator, which might not be as smart as a traditional software one just because of the restrictions of hardware. And then you kind of run this, you run the simulator on the test bench, and then you, from the simulation output, are able to feed some coverage info back into the test generator and kind of iterate that way. So the big issue with this is the custom test bench and the DUT modification, because this is a really time-consuming process, and this is why, even though the strategy is actually fairly effective at getting coverage quickly, it's had very low adoption because you can't convince a lot of designers to actually fiddle with the design under test in this way. And every time they have to test another thing, they're unable to reuse this test bench. They have to kind of create a new custom test bench for every design under test. If we take a closer look at what the actual hardware simulation is doing, it actually gives some interesting ideas on how we can improve this scheme from prior work. So you can see that the first thing that the hardware simulator does is it will convert this HDL into software binaries, and then it's going to compile it with a simulation engine that's capable of simulating how the hardware will behave, and then it kind of ends up with this hardware simulation binary, which is after you link all of these binaries together. And then now this is a software model where you're able to get that hardware simulation binary and then run your tests on it and get that info back, the coverage tracing info back to the test generator, and completing that feedback loop. So the authors of Fuzzing Hardware Like Software saw a really interesting opportunity here, where we can potentially get rid of this custom test bench by moving that test bench to much later. So after the actual design under test is made into a software model, and then at that point compiling it with a generic test bench to create the hardware simulation binary. So then on top of this, their idea is also to move where we're injecting the tracing. So you can see instead of actually touching the design under test, we're injecting the tracing, the coverage tracing instrumentation into the actual software model itself. And this way you kind of make the load on the designer as small as possible, because they just need to provide their kind of unchanged design under test. So if we clean up this first part, you can see we have this block that is turning a design under test into a hardware simulation binary with very little intervention. And then once it's a hardware simulation binary, since that's all software, it actually can interact with a normal software coverage guided fuzzer. And that's the key idea that we've been building to this whole time, where you can use a very mature and intelligent software-based coverage-based test generator, and you just plug in this hardware simulation binary, and you're able to do coverage analysis on this software-only side. So going back to our verification strategies, you can see that hardware fuzzing in some ways does get the best of both worlds, where you don't need a lot of designer time, but it's able to get deep testing and get it quickly on large designs in a way that older approaches had a much harder time doing. So when I was presenting that design, I kind of glossed over some big implementation challenges that need to be solved before you can actually pull this off. And one of the most pressing ones is that hardware inputs are inherently sequential. In other words, time matters, right? If you are using a software fuzzer, typically one file is just one run, but in this case, we have to somehow interpret a one-dimensional string of fuzzer bytes as some sort of spatio-temporal input sequence, and they design a generic harness that repeatedly maps these bytes to specific ports each cycle and make sure that it's able to test hardware in this way. Another kind of related one is figuring out how to detect if there is a hardware fault and then how to map that into a crash for the software fuzzer to pick it up. So to do this, they created a map where they kind of map these hardware faults to software crashes, and then they treat assertion or invariant violations as crashes that the fuzzer can triage, just like software failures. And this applies to, I guess, gold model mismatches if you're using a gold model. Another challenge that the authors had to deal with is how to actually know that you're achieving better and better coverage on the design editor test. So, in other words, like we care about coverage here, but we're only measuring coverage here. Like we're only measuring it in the actual design under test model, the software model of the design under test that's in this hardware simulation binary. So they had to argue that the better the software model is covered, the better the hardware is covered. And then also show that it's actually fuzzing the DUT as opposed to the simulation engine or the test bench. And I think in practice, they just put instrumentation for coverage in the design under test, and then they showed that empirically almost all of the time is spent in the design under test for a sufficiently large design. Another key challenge is how are we actually going to make this generic test bench and have it interface with any design under test, or the software model rather of any design under test. And to do this, they did something very clever where they developed like a very design agnostic testing solution that works at the standard bus interface. So pretty much all designs will interact with some sort of bus because no design really exists in isolation. So they made a very specialized bus transaction grammar and this special generic bus harness that is able to communicate to tons of different IP blocks or designs under test through this bus interface. The last challenge I wanted to briefly mention is that fuzzing only reports bugs that manifest as something you can automatically declare wrong. So that's the job of the test evaluator, right? And if the engineer is unable to provide a complete set of assertions and invariants, or is unable to supply some kind of gold model to work with, then this approach can't have the fuzzer deliver meaningful crashes. So it's still reliant on that last piece of the puzzle. And if a designer and their assertions aren't really complete, then it won't necessarily translate into finding a new security-related design flaw, especially if the bug is very subtle. So to conclude, I thought this was a really interesting paper that challenges some of the strongly held preconceptions about what a test bench should look like, and goes the other direction compared to past work, kind of making hardware more like software instead of the other way around. And we also saw that coverage guided tests are very applicable to hardware and can lead to kind of this best of both worlds where you can find deep states but also find them quickly in large designs. And lastly, that there's a lot of benefits to try to make the generic harness as reusable as possible, and they came up with a really clever way to use this like bus grammar to do that. And I encourage everyone to read the paper for more details, because I only covered a very small fraction of what they were able to do with this paper, but that's going to be it for now.